All right, so we'll get started with our first lesson of Unit 3, Probability Distributions. So to start, we're going to begin with a few different definitions, talk about a couple of things that we need to discuss before we get started, and then we'll do some examples. So throughout all of Unit 2, we looked at the probabilities of specific events and outcomes occurring. So we would look at a situation and we want to find a specific probability of a specific outcome in that situation. Now what we want to look at is the distribution of all of our possible outcomes. So we want to think about all of our outcomes and we want to assess the probabilities of all of these outcomes. We want to think about which outcomes are most likely, which ones are least likely. If I were to continue a game for a long period of time, what outcome should I expect? This also helps us to make estimates later on based off of different probabilities and different situations. So it's really taking our learning from Unit 1 and learning Unit 2 and taking it to the next step. So to start, a few definitions. First, we have our random variables. So we'll be looking at any random variable, and we'll denote that by capital X. For each of these random variables, we have a bunch of different outcomes with indices on them. So a random variable is the event or the situation that I'm looking at. Then I have all of my different outcomes, which would be denoted by x1 for the first outcome, x2 for the second outcome, etc., etc. Now, here's a quick example. So if x is the roll of a single die, so my random variable, denoted by capital X, is the roll of a single die, then we have 6 different outcomes. And we denote these by x1, x2, x3, x4, x5, x6. Now, x1 happens to have a value of 1, but it doesn't. x1 just means my first outcome. And it just helps us to keep track of all of our different outcomes, especially if we had a situation with many, many outcomes. Now, these random variables can be classified into 2 groups. First, we could have what are called continuous random variables. And these random variables have an infinite number of outcomes. So what that means is that decimals, fractions, all of those things are included and can be outcomes for this particular random variable. So, for example, this could include length of time. It could include a height measurement, really any sort of measurement where a decimal or fraction is a realistic answer. So for example, with a height, I could get a very good measuring tool and measure my height to 5 feet, 4.23 inches. The point is that the heights, you could be 5'3", 5'4", 5'4 and a quarter, 5'4 and a half. All of those numbers in between 5'4" and 5'5", all of those decimals and fractions that are in between those numbers are possible outcomes for this random variable. Now, we'll look at the opposite, which can help you to understand continuous random variables. So the alternative is to have a discrete random variable. And these random variables have a limited number of outcomes. So this means that not every single number on a number line is possible for a discrete random variable. So here's some examples to help you understand. We could have the number of stairs, number of people, dice outcomes. All of these examples, you can only have whole numbers. So for example, if I were to roll a single die, the only outcomes I can get are 1, 2, 3, 4, 5, 6. There's no way I could get 3.2 on a random die. So all of those numbers in between 3 and 4, they are not possible outcomes for my discrete random variable. I could either have 3 or I could have 4. All those little decimals in between, unfortunately, can't be real outcomes, and that's because it is discrete. So that's what those two things mean. Now, for the time being, we're going to primarily be working with discrete random variables, and then later on we'll talk about continuous ones and how that changes how we work with them. But for the most part, at the beginning of this unit, we will be looking at discrete variables. Now, the next definition, just a couple of things we need to talk about before we really get into the examples, is uniform probability. And it's important that we talk about uniform probability right away because it's important to always look out for uniform probability. So uniform probability is when the probability of all of our outcomes is the same. So it doesn't matter which outcome it is, the probability is equal for all of them. So for example, if I place the numbers 1 to 4 in a hat, the probability of any of these numbers being chosen first is the same. So that is an example of uniform probability because all of my outcomes have the exact same probability. Now we can actually write this out as a formula, and we won't use this formula too much today, but later on we will use it quite a bit. But we do need to be mindful of looking out for uniform probability. So for our probability, the probability of any outcome in our random variable, so the probability of x, our random variable, is equal to 1 over n, where n represents my total number of outcomes. And this is because all of my outcomes are equally likely, so we can just take 1 and divide it by our total number of outcomes. So that's our uniform probability. And like I said, we won't go through too many uniform probability questions today. We'll talk about it more later, but it is important that as we look at all of our different distributions that we put together, that we always look to see if they are uniform. It's really worthwhile to address that. Okay. So that is our first two pieces we need to talk about. And now we have one more. And this next one is the one that we're really going to use a lot and is really the main piece of our lesson today. So the last thing that we need to introduce today is what's called expected value. Now, expected value, denoted by E at X, so that's a capital X representing our random variable, is the predicted average of all of my possible outcomes. In other words, if this event happens over and over and over and over again, which outcome are we expected to get? If I kept track of all of the outcomes as this event occurred 1,000 times, what would be the average event that happens, or average outcome rather? So how we determine this is our expected value of our random variable x is equal to, we take our first outcome here and we multiply it by the probability of it happening. And we'll do this below to give you an example of how this works. Then we add this to our second outcome multiplied by the probability of that second outcome happening. Then we do it again. We add this to our third outcome multiplied by the probability of our third outcome happening. And then we would continue adding until we get to our last outcome, which we'll denote by xn, because n would represent our total number of outcomes. We don't know how many there are yet, so we'll just leave it with an n, and then the probability of that outcome happening. So again, x here is our random variable, and that's because we're calculating the expected value for all of the outcomes, not just one. And then xi are my specific outcomes that I could have. Now, as you could imagine, this formula could get very, very messy to write out, especially if I had 100 different outcomes with 100 different probabilities that I wanted to write out. So when we are adding a bunch of things like this, we use what's called sigma notation. And sigma notation is very beneficial because it condenses this long-winded formula, and different math softwares understand it, so it can help you to solve things without writing out this really, really long line of math. So here's how sigma notation works. My expected value of my random variable x is equal to the sum of, so this is a sigma, it's a capital sigma, which is a Greek letter. And in math, it represents the sum of a bunch of different terms. So we're going to sum up everything from our first outcome, outcome number 1, all the way to our nth outcome. So we're going all the way from n. So this funky symbol here means our sum from I equals 1 to n. Now, with this type of summation, you can choose any interval that you'd like to add up. So it doesn't have to be 1 to n. I could have had 1 to 5. I can choose whatever I want. Now, what are we adding up? We're taking each of our outcomes, xi, so that is our outcomes from I to n, and we're taking these i's as placeholders for 1, 2, 3, 4. And so we have that outcome, and we multiply it by the probability of that outcome. So that is our probability of, outcomes 1, I to n. There we go. So basically what we're doing is it's a short form of writing out this long thing up here. And it's just really helpful, especially let's say we had hundreds of different outcomes. This would help us just to keep track of things and write it out in a different way. Okay. We'll end up using sigma notation a lot in this unit. If you have looked up additional resources online, you may have saw these sigma things and gotten a little bit confused. But that's what they mean, and they end up being very, very beneficial. Okay. So the next thing that we're going to do is we're going to start with an example. And we're going to start working with our expected value just to give you a little bit more of an idea of what it is, how it works, all of that stuff. So our situation here, we want to determine the expected number of candies to be found in a candy bag based off of the given situation. So here's our situation. I want you to picture getting those little bags of candy on Halloween. So those teeny little bags of Fuzzy Peaches or Cherry Blasters or Sour Patch Kids, whichever one is your favorite. Now picture that I just have 40 of these little bags. Now within these bags is a bunch of candies. So what I'm going to do is I'm going to sort them all. I'm going to take all of the candy bags that only have 4 Fuzzy Peaches in it. I'm going to separate those from the bags that only have 5 Fuzzy Peaches in it. Separate that from the bag that has 6 Fuzzy Peaches in it, and separate it from the bag that has 7. Now I'm going to count out all these bags. So it turns out I have 11 bags with 4 Fuzzy Peaches in it. I have 9 bags with 5 Fuzzy Peaches in it. I have 12 bags with 6 Fuzzy Peaches in it, and then I have 8 bags with 7 Fuzzy Peaches in it. So this helps us to find the probability of getting a certain number of Fuzzy Peaches. Now we want to determine the expected number of candies. So if I were to pick a random candy bag, look at it and put it back, then I did that again, over and over and over and over and over again. What is the expected number of candies that I would get in the long run? So to do this, we need to first start by finishing up our distribution here. So we have all of our outcomes. We could either have 4 candies, 5 candies, 6 candies, or 7 candies, and we need to write out the probability. The chart that holds your outcomes and their probabilities is referred to as a probability distribution, That's what that chart is. We're going to make a few of these, but that's what that chart is. When we have all of our outcomes and all of their probabilities, that is a probability distribution. So let's find the probabilities of these. To start, the probability of having 4 candies per bag. There are 11 bags with 4 candies each out of the 40 total candy bags. So if I put that into my calculator, I will get 0.275. Next, I want to find the probability of getting a candy bag with only 5 candies in it. So there are 9 bags with 5 candies divided by the total bags. So that will give us 0.225. Next, we want to determine the probability of getting a bag with 6 candies. So there are 12 of those out of 40. Oops. And we will get 0.3. And then we want to determine the probability of grabbing a bag with 7 candies. So there are 8 of those out of 40. Gives us 0.2. Now, in this chart, which is my probability distribution, because all of my outcomes are mutually exclusive, I either have 4 candies in the bag or 5 candies or 6 or 7, there's no overlap between my probabilities, which means that all of my probabilities should add up to 1. So there's a check point here for you to check to see if you did everything right. So my probability should add up to 1 if everything went okay. Okay. So now we want to determine our expected number of candies in the bag. So this is where we use our expected value equation. So I'm going to start by writing it out. So our expected value of random variable x, which is counting the number of candies in the bag, we're going to sum up all of our answers. So we have x1, x1, x2, x3, x4. We want to sum up all of our outcomes from I equals 1 to 4 because there are 4 different outcomes. Then we take each individual outcome and multiply it by its probability. So let's go ahead and do that. So the first one, we take our first outcome and multiply it by its probability. There we go. Then, because we have that summation in front, that big sigma, also referred to as a summation, we're going to add everything. So then we add our second outcome multiplied by its probability. Then we add our third outcome multiplied by its probability. And then we add our fourth outcome multiplied by its probability. And then I put that whole thing into my calculator. So you should get 5.42. Now, as you can imagine, this could turn into a really, really big equation and calculation, but you can use math software to solve that. So I can show you how to do that on another day, but for right now, we'll just work on doing it by hand. So we have our expected value here. The expected value for number of candies is 5.42. So we would expect to have 5.42 candies in the bag on average. Now, here's the funny thing about our expected values. You may be looking at this and thinking, but we can't have 5.4 of a candy. We either have 5 candies or we have 6 candies. And if that is what you're thinking about, you are absolutely right. We can't have 5.4 candies. This represents the average number of candies we would get in the bag. So that means it's somewhere between 5 and 6 candies. And because 5.42 is pretty close to right in between our 2 middle numbers, it means that all of my different probabilities are all relatively close. It's not like it's skewed totally to one side. It's all pretty close in the middle. So on average, we should get 5.42 or somewhere between 5 and 6 candies in the bag. Are there any questions at all about this before we move on to the next one? I think we'll only be able to get through the next one, but that's okay. We're okay? I don't see any questions. Okay, so we'll do one more example together. And then the other ones you can try on your own and we can take up tomorrow. So for our next example, we're going to let x be a random variable that represents the number of heads that occur when a fair coin is flipped 3 times. Now, the old way we would have said this is we would have said, let event A be getting exactly 1 head on 3 flips of a fair coin or something like that. But now we want to assess all of the options and count how many heads we have. We want to look at the whole situation. So to start, let's identify the sample space just so we can find these probabilities a little bit better and fully understand our different outcomes. So the first situation we could have is we could have 0 heads. That's the first option. So I could have 0 heads. And I go through my sample space and there's only one option to have 0 heads. So that means 1 out of 1, 2, 3, 4, 5, 6, 7, 8 options is 0 heads. So that will give me 0.125. And of course, as always, you can keep that as a fraction or as a decimal. It doesn't matter to me. Now we'll do the same thing for 1 heads, and we'll talk about the next column in a second, so just bear with me for right now. So 1 heads, let's determine the probability of getting 1 head. So we have 1, 2, 3 different outcomes that only have 1 H. So 3 outcomes out of the total 8 outcomes. And that is 0.375. There we go. Then for 2 heads, we have 1, 2, 3. So 3 out of 8, which is 0.375. And finally, having 3 heads, 1 out of 8, which is 0.125. So all I'm doing is I'm finding all of our possible probabilities. Now this part here, this is your probability distribution. This chart right here. That's your probability distribution. I need your outcomes, what are they, and then your probability of each of those outcomes. That's what that is. Now what we're going to do is we're going to determine our expected value for this. So instead of writing it all out, very often you'll see that there's a third column added to your chart where we're just going to take the time to take the outcomes and multiply them by the probabilities. So then we can just add those all together to find the expected value. So that's exactly what I'm going to do. So we'll take 0, multiply it by 0.125, which is 0. And we're just going to continue in the same way. Times 0.375, which is 0.375. And then you just keep multiplying. Now remember, these are not probabilities. These are just us working towards getting our expected value. So it's not probabilities here. Okay. So EX, again, is called our expected value. And what it represents is the mean or average value of the outcomes of our random variable x. And we're going to weight them according to their probabilities. So again, our formula looks like this. And we'll get the hang of using it pretty quick. You'll all of a sudden pick it up and have no problems. So let's find our expected value for this particular situation. So I'm going to total up this whole column, right? That's the sum part. I've already done the xi multiplied by pxi part. So we have 0 plus 0.375 plus 0.75 plus 0.375, which is 1.5. Now, similar to before, you may be thinking, I can't have 0.5 of a heads with heads or tails. How does that work? Now, what this means is that when our fair coin is tossed 3 times, we expect we will get 1.5 heads over 3 tosses in the long term. So if I consistently do this, I should be right in between getting 1 heads and 2 heads. It should be right in between. So although I can't actually get 1.5 heads, it should be right in between there. Right in between 1 and 2 is my expected value. So the final thing that we're going to do is we're going to draw a bar graph of all of our probabilities. Now, I will be honest that sometimes these bar graphs, you don't really see the value when we have so few outcomes. If you choose to do any post-secondary statistics, you'll get some experiences with really big graphs with tons of outcomes. Even later in the semester, we'll use our graphs to give us a little bit more information about the situation, but the graphs are absolutely meaningful, even though here it's pretty clear to see what's going to happen with the graph, but we'll still do it anyways. So we're going to graph our outcomes with our probability of each outcome. So our outcomes here, this is my number of heads. I could have 0, 1, 2, or 3. And then the probabilities, they're all in decimals. Up to you how you want to use your scale. I just did this because it doesn't have to be perfect, but really up to you, whatever you'd like to do. Now, I'm just going to use their probabilities and draw it on the graph. So the probability of the first one, now remember, this is our probability chart, not this one. So the probability of the first one is 0.125. So we have 0.125. There we go. Oops. Now these aren't going to be perfect, and that is okay. We'll just do the best we can. That's the first one. And the next one, 0.375. There we go. Then we have 0.375 again. And finally, the last one is 0.125 again. There we go. So here it becomes very clear that getting 1 or 2 heads is far more likely than the others. And that they're even. So it does make a lot of sense that our expected value is right in between those. So again, like I said, the graph here seems not too exciting. It's a lot of stuff we could have saw from the chart. But long term, if I have more than just 4 outcomes, it will be very, very important. Now here's what you need to try. I want you to give these ones a go and give it a try. We'll see how things go, and then if people want to go through them tomorrow, we absolutely can. Our plan is just to introduce the project, but that won't take long. So we will certainly have time to go through a few more of these if people would like to. But there's no way we can finish that one right now. We'll leave it here where we are. Are there any questions about that drop date, about the unit, about this lesson, anything like that?